Let's talk some more about heat. As we mentioned before, heat is a transfer of thermal energy between a system and the surroundings, and it's going to depend on a difference in temperature. And just a reminder, temperature is a measure of the thermal energy within a sample of matter. So heat will flow from matter that has a high temperature to matter with a low temperature, and that heat will flow until both of the temperatures are the same. And then it stops. It's reached thermal equilibrium, and there's no net change after that. So you've got a cup of hot coffee, and you put 2 ice cubes in it. The coffee's hot. It's going to transfer thermal energy in the form of heat to the ice cubes. The ice cubes are going to melt and warm up, and when you're done, it's all at the same temperature, right? So when a system absorbs heat, the temperature goes up. We can say the temperature increase is delta T, the change in the temperature. That will be directly proportional to how much heat was put into the system. You put more heat in, delta T is bigger. You put less heat in, delta T is smaller. So we could write it like this: Q is equal to a proportionality constant times the change in temperature. And this constant would be called the heat capacity. The units would be joules per degree Celsius or joules per Kelvin. So the heat capacity is the amount of heat needed to change the temperature of that particular system by 1 degree. But the amount of heat needed to change the system by 1 degree is going to depend on how big the system is, right? If you're heating up water to make spaghetti and you're going to make a small pot of water or a really, really big pot of water, the big pot of water you're going to have to put a lot more energy into. The heat capacities are not going to be the same. In fact, every object pretty much is going to have a different heat capacity. So heat capacity is an extensive property. It depends on how much of the matter there is. So what's more useful is specific heat capacity. So this is C with an S. And this is the intrinsic capacity of a substance to absorb heat. So this is an intensive property. So the heat capacity of an object is going to depend on its mass and on the type of material. So specific heat capacity, amount of heat needed to raise the temperature of 1 gram of the substance by 1 degree Celsius. So the units are going to end up being joules per gram times degrees Celsius. You'll sometimes see a molar heat capacity, and that's the amount of heat needed to change 1 mole of the substance by 1 degree. Both of these are intensive properties. They don't depend on how big the sample is, like density. It's the same. So here's the equation that we'll be using. Q equals mc delta T. Come on. Q equals mc delta T. I've heard some students call it Q equals MCAT because the delta kind of looks like a capital A. So MCAT, whatever is good for you. So here Q is the heat measured in joules. M is the mass measured in grams. This is the specific heat capacity with units of joules per gram degree Celsius. And that's the temperature in degrees Celsius. So if we look at what's happening with the units, we've got the mass in grams times the specific heat capacity. So that's joules divided by grams and degrees Celsius multiplied by degrees Celsius. The grams cancel out, the degrees Celsius cancel out, and that's equal to joules. So this is a short list of some specific heat capacities of common substances. We've got elements, these are all metals. We've got a couple of compounds, and then some materials, glass, granite, and sand. And we see that water here has a specific heat capacity that's much larger than the rest of these. A lot of these metals are down below 0.5, and here's water above 4. That's a lot larger. You do not need to memorize any of these. But water has a very large heat capacity, which means that water can absorb a lot of heat energy without changing in temperature very much. And this has a big impact on local climate. So this photograph is of the San Francisco Bridge, Bay Bridge, right? So San Francisco's on this peninsula. It's surrounded by the San Francisco Bay and the ocean, and it only is, land on the one end, right? The weather in San Francisco is very different than the weather in Fresno. Even though in terms of longitude, we're about the same, right? It's not that they're so much farther north that they're so cool. But common temperature in the summer in San Francisco, 68 degrees. Fresno, 100. And we say, oh, this is a nice day. It's only 100 degrees Fahrenheit, right? Because I'm just glad it's not 110. Well, why is San Francisco so much cooler? It's all this water. So all of our heat energy is coming from the sun, and it beats down on us, and things warm up. Well, things like asphalt warm up a lot more than water. So if you think back here to sand on the beach, right? 0.8 is its heat capacity, whereas the water is a little over 4. So the sun shines down, and things like this rock and the bridge, they heat up. The ocean, the water, is also heating up, but it can absorb a lot more energy to have the same temperature increase. Or we could say it absorbs the same amount of energy, but only changes a little bit. So then the sun goes down, and now the air cools off, and we have warmer ocean and cooler air, and so the heat moves in the other direction, and heat moves from the ocean into the air. And so it's not uncommon for their temperature change from the high to low to be like 10 degrees. And here, it's not uncommon to have a 40-degree temperature swing in 24 hours, right? This is also why water is used as a coolant, like in the radiator of your car. There's a lot of friction with all the moving parts in the engine, and that heat builds up and can damage your engine. So you've got coolant running through the engine. The heat moves from the hot mechanical parts into the coolant. The coolant is pumped around to the radiator, which allows it to radiate all that heat away. And water works well for that because it can absorb a lot of energy without changing temperature very much. Any questions?
Yeah, the very first lab we did in my bio class was about like how water is used by life to promote overheating.
Yeah.
Keep the temperature nice and stable.
This high specific heat capacity of water is like, it's just really important in a lot of ways, because water is involved in our body regulating our temperature, right? What happens when you get hot? Well, you sweat, right? Then you become dehydrated. But you sweat, and as the water evaporates, it removes the heat, right? And helps you to keep your temperature the same. Okay, to determine whether a shiny gold-colored rock is actually gold, a chemistry student decides to measure its heat capacity. She first weighs the rock and finds it has a mass of 4.7 grams. Then she finds that upon absorption of 57.2 joules of heat, the temperature of the rock rises from 25 degrees Celsius to 57 degrees Celsius. Find the specific heat capacity of the substance composing the rock and determine whether the value is consistent with the rock being pure gold. So just like density can be used to identify a substance, specific heat capacity could also be used to identify a substance. So again, this is a problem that is just got so many words in it. I'm going to highlight the numbers. There's a fair number of those as well. And then the question, we want the specific heat capacity and then whether that is consistent with it being pure gold. Is there an easier way to figure out if this is gold? Yeah, we could find the density. It would be a lot simpler, right? So you put the rock on the balance, find its mass, you graduate a cylinder with some water in it, make a note of the level, put the rock in the water and see how much the water level goes up. There you've got the volume, mass divided by volume, density, compare it to gold. But apparently, well, it wouldn't, we wouldn't have this example, I guess, right? That's why I find this example a little bit annoying, but here it is. So let's take these numbers out and figure out what they are. So we have 4.7 grams, we have 57.2 joules, we have 25 degrees Celsius, and we have 57 degrees Celsius. They're asking for the specific heat capacity, so we probably need the Q equals MCAT equation. These are problems that sometimes require a unit conversion or so, but mostly they're solved with an equation. Dimensional analysis cannot solve all of our problems. So this says mass of 4.7 grams, and the unit gram should also clue us in that this is the mass. So I'm going to label that M. And it absorbs this much heat. So what letter goes with this one? 57.2.
Q.
Q. Mm-hmm. And then these guys are temperatures, right? So that's a temperature, and this is a temperature. But in the equation, we need delta T. Anytime you have delta something, you can assume that that means the final the final T minus the initial. So delta T is equal to the final temperature minus the initial temperature. So which one is the initial temperature? 25. And the final is 57. And we're relying on words and context, right? Temperature goes from 25 to 57. So if we calculate delta T, (32 degrees Celsius). So I have Q, I have M, I have delta T. What I'm trying to find is that C sub S, right? So I'm going to rearrange the equation. Oops. C sub S is going to equal Q over M times delta T. Now please come talk to me if you need help rearranging equations. A lot of students do. So now I can plug the numbers in with their units, of course. 57.2 joules is Q. The mass was 4.7 grams. The change in temperature, 32 degrees Celsius. So I got 57.2, and most students find it best to do this 57.2 divided by, now use your parentheses, open the parentheses, 4.7 times 32, close the parentheses, and press equals. And the units will be joules per gram degrees Celsius. Nothing is going to cancel out. This would have 2 sig figs, and so the answer to that first question, find the specific heat capacity of the rock, would be that. Yeah.
Is your, for the 4.7 and for the joules, is it joules divided by grams, or is that Q?
It's,
I'm just getting confused if it's a G or a Q.
this is a G,
That's a G.
and that's a G.
Okay.
Yeah. It's maybe not a very good G. Let me try again. Be a little more obvious. So how do we figure out if this is consistent with the rock being gold? We need to look up the specific heat capacity of gold. So we just go back to the table. And we got gold, 0.128, not gold.
It's always fake.
Yeah,
Never
you
trust.
just know it's gonna be fake.
Mm.
If you had to guess, what would you think it could be? It could be copper, because we came up with 0.38 and 0.385, that's, almost exactly the same. It could also be a mixture of a whole bunch of stuff.
Mm. Yeah.
Wait, I'm gonna finish this. So the rest of the answer is no, not consistent. Here's another example using the Q equals MC delta T equation. A 55-gram aluminum block, initially at 27.5 degrees Celsius, absorbs 725 joules of heat. What is the final temperature of the aluminum? Much less story in here, fewer words. 55 grams, 27.5 degrees Celsius, 725 joules. And we're looking for the final temperature. Well, let's pull our numbers out, write them down. So 55.0 grams. Let's make that better. Well, it doesn't say what that is, but what is that?
Oh, math.
That's the mass, right? Because gram is a unit of mass. And then it says initially at 27.5 degrees Celsius. So that's a temperature. Is that the initial or final? The initial. And then it says absorbs 725 joules of heat. So that's going to be Q. And is that positive or negative? It's positive because it absorbs, right? Money coming in is positive. And they're asking what's the final temperature? Well, we know that Q equals M C sub S delta T. So we've got Q and M, and we can look up the specific heat capacity of aluminum. But final temperature is not in that equation. But we could calculate the change in temperature, right? If we know the change in temperature is T final minus T initial. So if we add T initial to both sides, we find out that T final is equal to the change in temperature plus the initial temperature. So that's what we're going to look for. But first we need to find the specific heat capacity for aluminum. It's 0.9 something, 0.903. So now I'm solving for delta T. So rearranging this equation, I get delta T is equal to Q divided by M times specific heat capacity. So Q is 725 joules, and I've got 55.0 grams, and I've got 0.903 joules over moles. No. Oh, I did that again. Sorry. It's not moles, it's grams. It's not Kelvin. Sorry about that. Joules per gram degree Celsius, and joules per gram degree Celsius. So we do the math on the numbers. We got 725 divided by parentheses 55 times 0.903, close the parentheses, equals 14.597. And I should have 3 sig figs. Let's look at the units there. So I have joules divided by grams, and then I'm dividing by another fraction. If you're dividing by a fraction, that's the same as multiplying by the inverse of the fraction. Right? You upside down it and multiply. So I'm going to be multiplying by grams times degrees Celsius divided by joules. And then we can see that the grams cancel out and the joules cancel out. I highly recommend that you avoid dividing by things with fractions in them. Now, of course, here we have to do that. But, people are doing density equations, and they've got, some mass, and then they're dividing by the density. And they're saying, oh, well, the milliliters cancel out. No, they don't. That's times milliliters per gram. So you're ending up with a quantity that with units of milliliters squared per gram, which is nothing meaningful. What we should do instead is think of density as a conversion factor, and I'm going to multiply by grams and divide by milliliters so the units work out, right? And then I know I'd put my number in there. Okay, so I got sidetracked. I was grading worksheets. I saw that a few times. We don't need this anymore either. Didn't need to do that. Okay. Okay, so we found delta T, but we're not done yet. We want T final, which we said was delta T plus the initial temperature. There's delta T plus the initial temperature so we're going to call that 42.1 degrees Celsius. Do we expect the temperature to go up or down? Up, because this block is absorbing heat, so we expect the temperature to go up. If we messed up in here somewhere, we might have subtracted by accident and seen that the temperature went down, and then that would be a clue to look at our stuff. Any questions? .1.